Hello and welcome back to Calculus 3. So, section 11.2 on vectors in 3D now. So we're going to upgrade to the third-dimensional space. Before we do anything with vectors, we have to talk about 3D environment. You are familiar with the 2D environment because your past X amount of years of math, let's say 10 years of math, were all in 2D. You did the areas, you did the area of the shapes, the triangles, the circles, all of that, and then eventually in pre-calculus you got to your functions, where y is equal to f of x. X input, y output, 2 dimensions, 2D. All of the graphs are on the xy graph, right? So you are very familiar with 2D. However, you live in a 3D space. You are third-dimensional creatures. So that should be more natural to everyone than 2D. We experience 3D on a daily basis because we grab 3D objects all the time. We have depth perception, right? And we know we can move in 3D space. So the third-dimensional space is going to have 3 dimensions, x, y, and z, and those are dimensions of length. Again, I can make third-dimensional space with temperature, density, and time. That is 3D space, right? But it's not the 3D space that we are used to using and moving in, right? So if I'm talking about 3D space, I will draw 3 perpendicular axes, which obviously I cannot achieve on 2-dimensional surface, so you get something that looks like that. And in your perception, you will say, okay, there's a 90 degrees there, 90 degrees there, 90 degrees there, and then each one of these is 90 degrees. But if you really want to observe this, well, very simple, right there. There's one wall, the other wall, and the ceiling, and you have that corner, and that's going to be the way to understand what I just drew on the... Now, clearly you're going to do that on the floor, right, because this would be the floor, and this is the wall, and this is the wall. So they're 90 degrees to each other, and that constitutes the space that we live in. So now, before we go and do anything in this space, we are going to denote the x-axis, which would continue indefinitely on the negative side as well. The y-axis, which would continue indefinitely in the negative sense. And the z-axis, that would also go negative. The third-dimensional space has what we call... Well, let's first talk about this assignment. The way I drew this particular coordinate system, it's called right-handed. Right-hand coordinate system. Why? Because if you wrap your hand on the z-axis and you extend your thumb in the positive z direction, your fingers, as they wrap around z, are going to hit x first and then y. So the right... Do this now, guys. Let's go. Look at the screen and do it in your head. Wrap around. Look, as you wrap around z-axis, pointing up, you are hitting x with the fingers as you wrap, and then y. You also have the left coordinate system, which would have x over here and y over here. And now, as you wrap with the left hand with the thumb up, showing the positive z, your fingers hit x first. Tip of the fingers, right? Hit x first and then y. Is this important? Ooh, yes. Who's going to take AutoCAD? Yes, there's your first headache over there. when they hit you with the left-hand coordinate system. And I believe that's actually the default. but you might have to switch. It used to be, when I took AutoCAD R14, it was the left-hand coordinate system. My Calc3 and my statics class were both on the right-hand coordinate system. I was going crazy before I figured out what was the issue. All right? So it is important which coordinate system you have. So this is the left hand. We will be dealing with the right hand one. So that's that. Sometimes it will be beneficial for us to use different way to draw the coordinate system. Instead of doing what we have over there, we're going to do this. So certain objects will be better portrayed in this coordinate system. So let me do the little example over here. So if I have elliptical paraboloid, it's better to represent it here than in the other one. If I have a box, right, I want this one. So whether, it will depend on which shapes we want to represent. Again, we are representing a three-dimensional object on a two-dimensional surface. So it's tough, right? It's tough. You have to have perspective. You have to practice these things. Now, in a 2D realm, two axes, X and Y, used to cut your infinite R2 space in 4 quadrants. Now you are cutting with planes, which are walls, and you will be making 8 octets. So I have to show a picture of that from the book because it's annoying to draw this. It takes a long time. There it is. You see 3 planes. Orange plane, blue plane, and the green plane. Your origin 0, 0, 0 is in the middle over here. You have your X, Y, and Z axis. This is a right-handed coordinate system, right? So now, observe that the top has 4 rooms, because the green wall and the orange wall create 4 rooms, and then you have the 4 rooms on the bottom. That's 8 octets, right? 1 octet is the 0, 0, 0. Sorry, 1 octet is the first octet is one where they have all positives. So this room in front over here on top is the one with positive X, positive Y, and positive Z. And most of our stuff will happen there, but again, you have to know the whole thing. We are going to peek into all of them, obviously, but you have to know the whole thing because you are going to work on technical drawings, maybe, and you have to be able to find your way around. So now, as I draw this, X, Y, and Z, we can have our blue wall, we can have our orange wall, and as you can see, as you can't see, it's not as as fun to draw this thing here. We are talking about the intersections, so let me see where the intersections are. Maybe I can use the red one. From scratch. So X and then Y. There we go. Oh, you haven't brought a square notebook? Aww. You haven't brought the colored pencils? Aww. How am I gonna do this? I mean, if I do this, it doesn't show the floor. So I have to color the floor. The blue and orange. Oh, I know I can do. Eraser. Medium eraser. There we go. So blue is in front of that one, and then the orange is in front the blue one over here. And this is the line at which they... Alright, that would make sense. And then, since these are the axes, here and here, the ones that you can see, you can't see this line, can't see this line. Much better. And your floor would be here. So this is the space of one room. It's infinite though. Okay, great. So this is the one that it's facing us, and it has positive x. So that's the wall, and that's the floor. That's Z. And in this room, everything is positive. Point in R3, which is 3D, is given by X, Y, Z. Now, you will have to practice because you don't have enough experience with working with the 3D graphs, and you will need that in this class. Graph 3, 4, 7. All right, we can do this. X, Y, and Z. So what do I do? Well, I first count 3 down the x-axis. So the point I got to over here is 3, 0, 0, because I only moved on the x-axis. Now I have to go positive 4 in y direction. That better be along the line parallel to y. And I have to go 1, 2, 3, 4 units. So here, orange. And this new point that I have is 340. This point sits on the floor. That's 3, 4. So if you are trying to get to a point in 3D space, you first follow along the x-axis, and then you go 90 degrees parallel to y, and now we are going to go parallel to z. We need a construction line like this, and I need 1, 2, 3, 4, 5, 6, 7. So that will be the final stretch of the journey to get to 3, 4, 7. So you build it up. Go along x, go along y, and then go along z. Only x motion happens on the x-axis. The others are on the lines that are parallel to your y and z axis. Why do we have to do this? Because we are still having the same education as we had 400 years ago, right? Does anyone have Oculus Rift? All right. So have you played with the room where you can use the spray paint inside?
Yeah.
So you know what I'm talking about. Imagine if we could have that for every student in Calculus, and I say, okay, graph this point, and you can just go in a virtual space and actually looks real, right? So you can do these kind of things. So when you are looking at the course, you will always be staring at a 2D surface that is trying to portray three-dimensional reality. Maybe you want to make these things and try to make sense of them in real space, which is why I'm asking you to use the corner of the room as the reference for anything I say in class. So you want to create a right-handed system that will work all the time, and you can refer to, and if I'm talking about something, you didn't get it, you just look at the corner. What do I have for the right-hand system? That wall will have x-axis as a base. So along the base of the wall where the door is, you will have x-axis going that way to positive infinity forever. This is your y wall. Y-axis is the one on the floor going all the way that way to positive infinity. Z-axis is going up along the blue line. Blue line, that's the green line. The green line going up, that's your z-axis. So look, wrap around, you're hitting your x, you're hitting your y. So x, y. So it's a right-hand coordinate system. We have to keep that wall to be x, this wall to be y, that to be z. I mean, not the wall. Wall is not x. That's the plane. That's the xz plane. But it's along the base of the wall is the x-axis. So when I am talking about the point 347, I can find the exact location of 347 in this classroom, because right now I'm standing at 0, 0. I need 3 feet. Look at the ceiling. What is the ceiling? Ceiling are these tiles of 2 by 4. So I need to go to the middle of this vent over here. That's 3, and I just walked on x-axis 3. And then I need to go, because this is 2 feet, I need to go 4 feet forward, which is exactly here to the end of this table. And since I'm 6 feet tall, 6'2", but 6, right? Add another foot. It's right this point here, the one that we draw, right here. So if there is a bug right here, the location of that bug is traced in a 3D system as 347. And we are going to stretch a vector to that position to trace the position of that little bug from the origin, and then that bug is going to buzz around, and we're going to create a vector function that will follow it, and it will create a path in the 3D environment. You have to understand, we're going to build up a lot on this. This one single point is a single instance in time. We're going to strike a function through that. and we're going to trace it at all times with the vector valued functions. That's next week. So it's coming up. If you're having issues visualizing 3D, my argument is you shouldn't because you live in 3D space, but if you have issues in visualizing this, you have to beat that by playing with real things. Stretch your measuring tape at home, because you most likely don't have a ceiling like this that gives you a perfect grid. Stretch the measuring tape and figure out where the points are. Also be very careful, the right system and the left system, because you want the X and then Y, and you want 90 degrees. You don't want 270 on the other end to create these kind of things. So you travel along one axis, another axis, another axis to get to the point, and you are able to find location anywhere in space. Now, I talked about the walls already. We've seen the attempt to draw the room, right? The coordinate system will have these three basic planes. The plane of the floor is going to be called the z equals 0. It's the xy plane. So, basic planes. Floor. It's called the xy plane and has equation z equals 0. Wall on x. That's the xz plane with the equation y equals to 0. And wall on y is a yz plane, and I call it x equal to 0. You have seen these types of equations before in a 2D realm. Remember in 2D, when you had your horizontal and a vertical line? So your vertical line had the equation x equals 2. And there was no mention of y at all. So it was just x equals 2. Because it's x equals 2 for any y you can think of. Y's are from negative infinity to positive infinity. The y is not mentioned in the equation because it takes on all of the values. Here we go with the y equals 1 horizontal line. Y equals 1 horizontal line is for all x's. So from negative infinity to positive infinity, y is pinned to be 1. So now if you go back and look at these equations of the plane, you see that z equals 0 is xy plane. Because z equals 0 is important to tell you at which elevation you are, but it's for all x's and y's to go to infinity. So that's why we don't have x and y mentioned in the equation for the floor. Because the floor is the 0 level for this particular environment, this room. What's the ceiling? Ceiling equation is z equals to 10 because it's 10 feet away from the floor. So now, if I draw this classroom, and I paint this wall green because it's painted green. This is the classroom you're sitting in. So what do I have? I have a door right here. Put the handle on the wrong side. There we go. So this is your door. This is where the whiteboard and the projector are. So what do we have? First off, I have the floor. Floor is equation z equals 0. And then I have the ceiling. And that is going to be z equals 10 because it's 10 feet away from the floor. Observe that there are no x and y in the equation for the ceiling or the floor because it extends indefinitely. You say, wait, but it doesn't go indefinitely. Yes, because the other walls stop it. So each one of these will cut the other one from going to infinity. And then you make the shape and the bounded object. So if I am to put only the floor and only the ceiling, there we go forever. So now I am going to go to my, what I called the wall built on X. Wall built on X is the one with the door because that's my x-axis. So this wall over here, which is on the x-axis as I labeled it in the classroom, so this wall is going to be y equal to 0. That's the y equals 0 wall. Now, what's the other wall on the other side that has windows on it? So this over here is the wall with windows. What do I have for this wall? What's the equation? I need you exactly to tell me how long this is. You know. He knows. I saw him. I saw him calculating. Exactly 36. Very good. How does he know it's exactly 36? You didn't see him drive to Home Depot to buy the measurement. Exactly. Tiles on top. 2 feet each, one counting. Right? So you have to be observant, right? So you said 36, so I think it was 34. 17 tiles? Okay. So we have 17 tiles across times 2 feet is exactly 34 feet. Well, there you have a little bit and a little bit, so probably 35. Right? 35 feet. So y equals 35, guys. That's the exact equation for that wall. This is how you build stuff. Right? That's that. This is the wall where the whiteboard is, the front of the room. This wall over here is on y, so it's x equals 0. So what's the green wall in the back? Thank you. X equals 28. There you go. That's how you mathematically describe this classroom. So what do? Well, you go home and you annoy someone in the house with this. Sit them down and you practice, and you explain how the room you're in has these types of bounds. So what do I have? I have the xy plane, which is the floor, and another xy plane, which is the ceiling. Z equals 0, z equals 10. Then I have that wall over there, that's y equals 0, and y equals 35. On that side, x equals 0 here, and x equals 28 in the back. The measurements are found on the ceiling because we have the tiles that are 2 by 4. You can calculate the tiles, how many tiles you have. So we have apparently 7 this way and 14 this way with those 2 little slivers to make up for the difference. Great. So we are Now understanding, hopefully, the 3D space, we understand how to locate the point, and we hopefully also understand how to bound this space in its most basic shape, which is a box. So now we want to decide a few things. One of them is the distances in Hello? Oh no, who died last week? All right, let's go. I don't have a brother. I have a sister. So the distance. This is Euclidean space, which means it's a flat space. The distance is going to be calculated using the same square root formula for distances. So if I have the distance between 2 points in 3D space, distance d will be calculated as the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. And if you are to cover up this part, what you see is the formula for 2D distance. From here, it shouldn't be very difficult for you to extrapolate the formula for 4D. Just add another W term at the end and keep the pattern. So we can find the distance between 2 points by simply using the distance formula. And guess what? This is going to calculate your magnitude of the vector later, right? Because position 1 is your initial point and position 2 is your terminal point. So you will use this to determine the magnitude of the vector. So you need this, right? That's the distance. And I believe we need to talk about the sphere as well before we... Yeah, so we have the midpoint as well. And midpoint is going to be the average of all. So midpoint is going to be given as x1 plus x2 over 2, comma y1 plus y2 over 2, and then z1 plus z2 over 2. So this is what we have. We have the distance and we have the midpoint. And since we talked about the box, we will talk also about the sphere, one of the basic shapes. It's actually a perfect shape. Sphere is also known as a ball. And we have equation of x squared plus y squared plus z squared equals r squared with the center at origin. So center at 0, 0, 0. Now I can also move that center somewhere else and have x minus a squared plus y minus b squared plus z minus c squared equals r squared with a center at ABC. Again, note what happens. Tell me, what am I talking about now? Circle. Thank you. So you introduce the term, it's a ball, remove the term, 2D circle. All three formulas over here, you see that you had them in 2D space, and you just added another variable, another dimension to it, and made it into 3D. And a lot of Calc3 stuff will actually be upgraded that way. You just add another thing at the end. So now we have this. So we have the, we talked about the box, we talked about distance, midpoint, sphere. So we should be good to go to do some actually vectors, which is the title of the whole lecture. So vectors in 2D, vectors in 3D. So in R3. So we cut and paste everything from 2D, except the direction. It is not easy to work with the direction in a 3D space. You have to come up with a direction that is relative to something else. You will have the direction in XY plane, direction XZ plane, direction is in YZ plane, and calculating all those independently for the purposes is just not something that is efficient. There are certain things that are called directional derivatives, which we are going to use. And another thing that this book is actually not dealing with, which are called directional cosines. So, for whatever reason, we are not discussing the distance. The direction. We are discussing the magnitude of the 3D vector. It beats me, why? I don't know. So, when you have a vector now, PQ, and it's called the vector U, your vector U is going to have three components because it's a three-dimensional vector. Dimension per variable. And what do we do with this? Well, everything is the same. You are going to have the component notation U1i plus U2j plus U3k. Blue. All of the properties from 11.1 are the same. I'm not going to write those 10 properties again. Your magnitude of vector U is going to be given by the Euclidean distance again. We don't deal with direction. I told you about that already. But I need you to know, especially if you go to your physics and statics classes, that there are ways to deal with the direction for 3D vectors. If you want to explore those, please stop by. Yes? Oh, the arrows are not supposed to be, yes. The arrows are not supposed to be in the square root. Thank you. Yes?
There's supposed to be squares in each of the units.
That's what I wanted to put. I wanted to put squares and I put arrows instead. Very good. So, we are going to find vectors again by subtracting, and this skill is very important, guys. So if I give you a vector, a point P, to be 3, 0, and 6, and I give you Q as 1, negative 2, and 4, what is the vector PQ? What is the vector QP? Okay, so to find a vector, it's terminal minus initial. So for PQ, we have terminal, which is 1, minus 3. Terminal, negative 2, minus 0. Terminal, 4, minus 6. For a total of negative 2, negative 2, negative 2. PQ, no, QP. Well, we know that it has to be 2, 2, 2, right? But let's go terminal minus initial. 3 minus 1, 0 minus negative 2, and 6 minus 4. For a total of 2, 2, 2. All of the properties are the same. We add the same way, scale the same way, do all of those things. So add, subtract, scale, the same as in 11.1. What am I going to care about the most? The unit vector, right? So, unit vector is always defined as the vector divided by its magnitude. And I'm serious, learn this formula or quit. Quit Calc 3, you're done. So if I give you the vector u as 2, 3, 6, and I'm asking for the unit vector, you will calculate the magnitude and then divide each of the components with that magnitude. You will either provide the answer as a decimal, or you will provide the answer as the exact answer without square roots in the denominator. So one of the two options for full credit. The square roots left in the denominator is minus 1 or minus 2, depending on whether it's exam or lab. And it's not because I'm evil, it's just because you cannot submit square roots as your answer for machining, or you can do division with it. What are the chances? I picked random. Alright. Fine. This is your unit vector, which means magnitude is 1. You can check, square each one of these and add them. You will get 49 over 49, and that's 1. Where are we going to use this? Again, we live in a 3D environment. So 3D vectors are more important than 2D vectors, right? Think about this. To get a plane, airplane, to go from one location to another location, there's a lot of calculations you have to do, and you have to do it right. But when you do those calculations, you still have factors that you have to correct for, like wind. So if you are flying in a direction that you want and need to reach your destination, and you have a crosswind that is hitting your plane sideways, you have to correct for that. Otherwise, you're going to end up on a totally different spot. This is a really cool website that we are going to take a look at now. There we go. United States. There we go. Here. This is the live feed for most of the commercial flights. There's wind everywhere. So when you look at this mess, each one of these is guided in 3D. You're not having, Timmy sitting down calculating this by hand. You write software for this to track. Do we have any computer science here? That doesn't you. I know. No one else? Okay. So this is what you write the software for. You gotta make sense out of this. These people need to land. These people need to take off. They need to get places. We are crashing one airplane into another. So the destination between the two continents, right? There we go. Busy bees, right? Look at that. You have destinations. You are going to have a vector that stretches, and then when the wind hits from the side, remember sum of all forces in all directions is equal to 0 and so on. It's exactly what you have to use to correct back to the direction that you want. This is why people don't fly anymore. Pilots don't fly, machines fly, because it's much more efficient to do the navigation and controls than for a human to do this. Ships, same thing. Yes, they're bouncing on water, right? So it's technically through 2D, but then think of submarines, right? Which also have to worry about the height. So, and currents of the, right, where they are. This is extremely complicated, guys. It's extremely complicated, and obviously lives depend on, right? So you have a 3D system because you are on a 3-dimensional ball, and you have to worry about the X and Y and Z if you're talking about airplanes and submarines. So that's the place where you would use these types. And obviously to construct the structures, make sure that all forces check out, to make machines and everything else. Cool. Questions, concerns? Nothing? Yes?
And we just have to do 11.1 and 2 on the.
Yes, I'm going to start the homework.